Hello, Assalamualaikum.
Salam, thank you.
Sorry lambat approve.
Oh, tak apa.
Sorry
Kan ada masalah apa-apa.
tak ada sebab dia tak keluar notification pun sebenarnya Deflection dah buka. So cerita dia.
Okay.
Anything boleh tanya sekarang kalau nak.
Baik.
Hello, Doctor.
Hi, Rokman. Is everyone here? Not yet, right?
No, we're still waiting for a few people, including Dr. Leo. Kejap Dr. Leo minta saya link.
Dr. Dudo sudah ada. Miss Aminato sudah ada. Dr. Kuzama kat mana? Mungkin kat Padani kot.
Baru masuk.
Baru masuk?
Ya, dia. On the way.
Alright. Dr. Kuzama ada. Dr. Juan dah ada? Tidak.
Belum. Dr. Juan belum lagi.
Yeah, Dr. Leo is in.
Hi, I'm here. Sorry, not familiar.
No problem, it's okay.
No problem, Doctor.
So I think, so semua orang sudah ada kan?
Dr. Juan saja, but we can proceed with our usual presenters.
Okay. So I start yang bawah dulu lah.
Okay, sure.
Okay, salam sejahtera and very good morning, ladies and gentlemen. Welcome to the first Malaysia International Conference on Nanotechnology and Catalysis, MICNC 2021. So we are now in the sections photochemistry and electrochemistry. So my name is Morris. So I am your chairperson today, together with the section moderator, Ms. Nurul Asri, and also Mr. Muhammad Lukman. So I invite all the invited speakers and presenters to request to share audio and video now. All right. I would like to seek for your kind of cooperation to mute your mic if you are not presenting and to avoid any kind of virtual disturbance as possible. So for those who intend to ask questions to the presenters, you can channel your questions in the chat box, right? So I will read after every presentations. You can also request to share your audio and visual to ask you questions in live mode, okay? So before we start these parallel sections, I would appreciate if everybody can turn on the camera for a photo sections. Ada? All right.
Dr. Morris, should we wait for Dr. Juan?
Dr. Juan kat mana ni? Dia masuk ke tak masuk?
Tak apa lah, biar.
Okay.
Ambil
how about we do this? At the end, we'll do another one. At the end, we'll do another session.
Nanti Dr. Juan masuk, kita buat satu lagi lah.
Okay. At the end then.
Okay.
Okay, thank you, Doctor.
Alright,
I'm taking your pictures. 1, 2, 3. Alright, thank you.
Alright. Okay, since the evaluator is here, presenters also here. So without further delay, so I will start the session lah. Okay. So without further delay, you will be hearing a presentation from Miss Aminato Sobira binti Jahari. And the title is Dielectric Properties and Piezoelectric Constant of Electrospan Pvdf with different molecular weights. Please welcome.
Doctor, and thank you, community. Assalamualaikum. Assalamualaikum and very good morning to ladies and gentlemen. Electron span polyvinyl fluoride, PVDF, a semi-crystalline polymer with excellent properties like high flexibility, lightweight, and high piezoelectric constant. It has been used in many applications such as sensor, actuators, capacitor, medical devices, and also smartwatch. The beta phase of PVDF is particular interest as it is essential to obtain piezoelectric properties. Here, I am Aminatul Sabirah binti Zahari, a postgraduate student from Faculty of Industrial Science and Technology, University Malaysia Pahang, and my topic is dielectric properties and piezoelectric constant of electrospan polyvinyl fluoride, PVDF, with different molecular weight. So I would like to discuss about crystalline phases of PVDF, followed by an objective, step to prepare PVDF with different molecular weight, their characteristic, and last but not least, a conclusion of my study. Now, let's move on to the first topic, crystalline phases of PVDF. There are two well-known crystalline phases of PVDF, alpha and beta phases. The beta phase is desirable phase to produce high piezoelectric constant and high dielectric properties, or in other words, can improve electrical properties. The alpha phase is not an electroactive phase. The objective of my study is to study electrical properties of electrospan PVDF with different molecular weights. So PVDF can be synthesized by using three types of method. First, solution casting. Second, speed coating. Third, electrospinning. Solution casting promotes the beta phase formation after adding zinc oxide. While for speed coating method, beta phase is dominant up to baking temperature of 60 degrees Celsius. However, more than 60 degrees Celsius, beta phase decreases. Besides that, electrospinning yield electrospan nanofiber with higher content of beta phase and also produce good features like and lightweight. Because electrospinning produces the highest beta phase PVDF, we chose electrospinning to synthesize PVDF with the low weight. Next, in this work, we prepare PVDF with 4 different molecular weight. We use 4 types, which are 180,000, 275,000, 530,000, and 1 million gram per mole. First of all, we will dissolve PVDF into the mixed solvent of DMF and acetone. DMF is stand for dimethyl-formamide. And the solution was for 12 hours at 60 degrees Celsius. Then 10 ml of PVDF solution was placed into the shrink to produce membrane nanofiber electrospinning. Lastly, the third image shows the end product of electrospinning called as the electrospan PVDF nanofiber membrane. After that, all membranes were characterized using FISM, SRD, FTIR, whereas DT3 and EIS were used to study about electrical properties of PVDF. Now we have seen preparation of electrospan PVDF with different molecular weight. Let's see the characteristics of PVDF. From the FISM image, the average diameter increased when the molecular weight of PVDF increased. The PVDF for 530,000 gram per mole display the widest diameter because of unstable electrical force during electrospinning. Second, based on FTIR graph, the beta phase was found most frequently in all PVDF membrane. That phase was developed successfully by electrospinning. So from the FTIR data, we can calculate the fraction of beta phase in PVDF by using equation 1. When molecular weight increase, the beta phase decrease. The highest beta phase is 80.25%, belongs to the sample PVDF with molecular weight 180,000 gram per mole. Third, the SRD spectra. The lowest molecular weight shows 2 peaks of beta phase, and it also has the highest crystallinity compared to other molecular weight. So we can say that the crystallinity is related to the beta phase content because The lowest molecular weight contain the higher crystallinity as well as beta phase content. Next, in order to study the effect of molecular weight on the electrical properties of the membrane were evaluated by EIS and DT3. The lowest molecular weight has the highest dielectric constant, which is 2.6, because it has high beta phase content. Same goes for the piezoelectric constant. The lowest molecular weight has the highest piezoelectric constant, which is 21.0 picocoulomb per Newton. Thus, piezoelectric constant and dielectric constant are affected by molecular weight. In a conclusion, high content of beta phase in the lowest molecular weight, which is belong to 180,000 gram per mole, resulting high dielectric constant and piezoelectric constant. And it is ideal molecular weight to produce good piezoelectric constant. I would like to thank University Malaysia Pahang for laboratory facilities as well as financial support for this project. Here are my references throughout my presentation. Now I leave you with a quote from Edward Teller. The sign of today is the technology of tomorrow. And with that, I thank you.
All right, thank you very much, Ms. Aminato, for addressing this interesting topic. So, ladies and gentlemen, now we come to Q&A sessions. Please mention your name before addressing your questions, and I will raise the questions from the Q&A box as well.
Hi, my name is Nur Azri Kalisa. Can I ask what question?
Yes.
Yeah, sure.
Okay. So I want to ask whether just now you mentioned molecular weight affect the does give effect to beta phase, right? So is there any other reason for to change the beta phase?
The other reason is the method we prepare the Pvdf.
How about if adding any fillers or maybe any treatments like heat treatment or?
Actually, during electrospinning tu, we charge the polymer Pvdf solution tu. That's why from the alpha phase change to the beta phase in Pvdf. In the next work, we can add filler or additive to improve the beta phase content also.
Oh, okay, thank you.
Any more questions from the floor? Yeah, Miss Aminato, I have a question actually. Yeah, Tutorial, please.
Maybe just a brief one. May I know the novelty of your work? Maybe you can briefly tell us about the novelty and also the practicability of your research. Thank you.
Thank you, Tutorial.
Thank you, Maurice.
So the research is about increase the piezoelectric constant of Pvdf after using electrospinning method. And second, encourage formation of the beta phase, which is, we know that beta phase is influence the electrical properties of Pvdf. And the third is we successfully produce high beta phase content. And the last one is also we can increase the voltage output when we use piezoelectric constant.
About the practicability use of your research, is it any potential to commercialization or turn it into a potential products? Yeah.
Potential product, it can be used. Okay. Potential product, it can be used in gas lighter or sensor, in microphone, or in smartwatch. As a sensor lah, especially.
Okay,
because
thank you.
It's okay.
All right, Miss Aminato, one more question from me. You are using the electrospinning method, right?
Yes.
For your synthesis, and is this any other methods to do the similar studies, or why you choose the electrospinning method? Because it seems, is it low cost or easy to prepare? What is the chemistry behind you are choosing the electrospinning methods to prepare your samples? Thank you.
First of all, I chose electrospinning to prepare electrospun Pvdf with different molecular weight because it is cost effective and also it's easy to handle when we prepare the because by using electrospinning, it can produce lightweight electrospine nanofiber and also is produce high flexibility, which is easily to install. Depends on our application.
Let's see. All right. Any more questions from the floor?
Okay, Assalamualaikum.
Dr. Asmadina, please.
Yes, good morning. Okay, thank you, Ms. Aminatou, for the very interesting presentation. Okay, may I know what else that you need to do before you can commercialize your finding here, your research here? I mean that future research that you tend to do in order to expand more for your research here. Thank you.
To extend more, I would prefer to use additive like cellulose nanocrystal because cellulose nanocrystal also produce high tensile properties, which is can improve the poor Pvdf electrospine properties also. And then I still will use the CNC add to the Pvdf by using electrospinning because it also can improve the beta phase formation in the Pvdf. So in general, I will use any filler or additive to introduce into Pvdf.
All right, thank you, Ms. Aminatou.
All right, thank you, Ms. Aminatou. Okay, now moving along to our next presenter, please welcome Dr. Guzama Arifin. And the title is Photoelectrochemical Hydrogen Productions of TiO2 COS Composite. Please welcome.
Okay, folks, I'll be playing Dr. Huzaima's pre-recorded video.
Okay.
So just inform me if anything's missing, anything's wrong. Just give a shout out. Thank you, everyone.
All right.
Assalamualaikum warahmatullahi wabarakatuh, and good morning to everyone. I'm Huzaima Arifin from Fuel Cell Institute, University Kebangsaan Malaysia.
Sorry, 1 minute. Let me go full screen.
Today, I will present my research with photocatalytic hydrogen generation from water molecule using TiO2 COS composite. This is outline of my presentation today: introduction, materials and methods, results and discussion, and last conclusion. The background of this study is related to the energy issues. As we know, electricity is one of the most crucial things to support our modern life for transportation, industry, telecommunication, and so on. And the number of electricity needed increase day by day. Fossil fuel as today's primary electricity source will run out soon and cannot be renewable in short time. Besides that, the fossil fuel combustion also release CO2 and other greenhouse gases which affect to global warming. Hydrogen has been considered as a future energy carrier to replace fossil fuel. Hydrogen used in a fuel cell system produce electricity with the only byproduct is pure water. It is a clean way to produce electricity. However, hydrogen cannot be found naturally as a hydrogen gas on Earth. Hydrogen binds with other elements, such as with oxygen in form of water molecule, binds with carbon as a hydrocarbon molecule, and with other elements in form of acid or base molecule. So that hydrogen need to extract it from that sources. And the water molecule that is free and available everywhere can be ideal source of hydrogen. But to split the water molecule to hydrogen and oxygen also need high energy. It's about 237.2 kilojoule per mole. So we need hydrogen to generate electricity, but the other side, we also need high energy to produce hydrogen. To solve this problem, we need to use energy from renewable energy source. And one of them is by using sunlight energy through direct photoelectrochemical method. In the PEC method, water molecules split directly in situ with a simple and space-saving system compared to conventional solar hydrogen system, which employ electrolyzer and PV panel. This is this PEC method for water splitting first time reported by Fukushima and Honda at 1972. They used TiO2 as a photoelectrode material, and until now, this hydrogen production method is still under research because the efficiency and stability of the photoelectrode is still below US DOE requirement for commercialization. There are several requirement material to become a photoelectrode. The material should be photoactive. And then the photoactive material should have a band gap bigger than 1.23 electron volt and less than 3 electron volt. 1 to 3 electron volt actually is thermodynamic redox potential of water. Meanwhile, if the band gap bigger than 3 electron volt, the efficiency of the system will be very low because the photoelectron need high energy to work. And photo-generated electron and hole are easy to recombine. Besides the band gap, band edge position also important.
Sorry, just want to confirm, screen gelap ke? Is the screen dark? Can anybody respond?
Sekarang no?
Nampak sekarang. Tadi video okay tak, Doktor?
Kalau video okay.
Tadi video okay. Sorry then. False alarm. Sorry.
The conduction and valence position should be straddle to reduce potential of water molecule. So actually, not many semiconductor material fulfill that requirements. The material with ideal electronic structure, such as selenide based material, are very expensive because the availability is very limited. TiO2 still become material that interesting to study as photoelectrode until today. TiO2 has several advantages: photoactive, good photo and chemical stability, non-toxic, cheap, and abundant. However, TiO2 has 3.2 electron volt. It means TiO2 only can utilize UV energy. As we know that amount of UV energy only around 4% of solar spectrum. Meanwhile, the majority energy that is visible light with amount around 40% cannot be utilized. The white band gap also causing photo-generated electron and hole are easy to recombine. That's why the maximum photocurrent density able to achieve of TiO2 is only 1 milliampere per cm square. There are a few methods to overcome the wide bandgap problem. One of them is by adding co-catalyst. The presence of co-catalyst not only to conduct such reaction, but also to form a heterojunction band structure. The suitable heterojunction supposed to reduce the charge recombination. In this study, we evaluate photocatalytic water splitting performance by using TiO2 COS composite. Why we choose COS? Because COS is an electrochemical active material, cheap and non-toxic compared to other metal carcinogenic. The composite in this study was synthesized in few steps. The first synthesis of COS by using hydrothermal method. The COS powder result from the hydrothermal methods, then mixed with TiO2 degussa to form TiO2 COS composite. Since the composite is in chance form, we need to crush it to become nano size with bone milling. After that, the composite case on FPO glass and used to characterization. Okay, we go to the result in discussion. In this study, we report the performance of three variation composition of TiO2 and COS, M10, M20, and M30. The name of the sample names are representative of COS with percentage in the composite. This is the extended spectral analysis of M10 compared to related TiO2 and COS. We can see clearly that the peak of COS is already present in the M10. Here we only report the XRD for M10, which has the lowest content of COS compared to other sample. So if we can detect COS in the M10, so we can show that COS also already in the two other sample. Okay, this is efficient image of M10. We can see the sample forming porous and uniform particle shape of nanosphere. The nanosphere size produced is very small, around 30 to 50 nanometer. The efficient EDX shows the peaks of titanium, oxygen, cobalt, and sulfur. The presence of cobalt and sulfur element in the EDX characterization also confirms presence of COS in the sample. Okay, this is optical properties of the samples. Figure A and B shows the absorption and gap determination of the sample. The pure TiO2 absorbs the lowest light energy compared to all composite samples, and the band gap value about 3.3 electron volt. Meanwhile, the band gap of M10 is slightly lower, about 2.26 electron volt, while band gap of M20 and M30 are 2.83 and 2.72 electron volt respectively. The reduction of band gap energy due to increasing the sensitivity of the TiO2 to the visible light with the presence of COS. As we know, the COS able to capture visible light energy better than TiO2 because it has smaller band gap. This is the MICNC plot from EIS result. Shows the value of resistance of the sample. M30 has the smallest cycle actually, whereas the pure TiO2 has the largest semi-cycles. The result from EIS agree with the band gap calculation result. The Morse-Schottky plot were calculated from the EIS result used to determine the charge density and electronic properties of the sample. Okay, the highest charge density in the study produced by M30 sample. Okay, The combination of the electronic properties describe the ability in the photocatalytic water splitting process, where the band edge position and band gap of the composite become more appropriate for the photocatalytic water splitting of hydrogen generation compared to related TiO2. Although the result here is not very significant. This is the photoelectrochemical performance and hydrogen generation measurement. The photocurrent density of the sample was determined using linear sweep voltammetry (LSV). We can see that all the composite samples produce higher current photocurrent density compared to pure TiO2. The highest photocurrent density shown by M3 sample about 0.32 milliampere per cm squared at 0.94 versus AgCl. The value almost 10 times higher than that of the pure TiO2. The pure TiO2 in the study produced about 0.03 milliampere per cm squared. Meanwhile, the highest photocurrent density M10 is about 0.16 milliampere per cm squared at 0.44, and M20 is 0.18 milliampere per cm squared at 0.654. The magnitude of the photocurrent density of the composite indicates that the number of electrons generated that will involve in the hydrogen production reaction. In the study, the hydrogen generation was performed in homogeneous system using composite powder in photocatalytic reactor, and hydrogen detected using hydrogen sensor. The highest hydrogen production rate of pure TiO2 is about 0.154 millimole per hour per gram. Meanwhile, the highest hydrogen generation obtained by M30 sample with the hydrogen rate about 0.41 millimole per hour per gram. It's about 3 times higher than pure TiO2. If we compare to the similar study reported by New et al. 2018, they found that hydrogen produced by 20% COS TiO2 composite is about 5.6 millimole per hour per gram, which is 65 times higher than 67 times higher than pure TiO2. However, in the study, in their study, they add methanol 76% as a sacrificial electron donor to the reaction. Meanwhile, in our study, we only use 0.4 molar of sodium sulfate solution without adding sacrificial electron or proton source like methanol. So we can say that the hydrogen in this study was produced purely from the water splitting molecule and not from the electrolyte or the other source. For the conclusion, the overall result in the study indicates that the presence of COS could improve the photocatalytic ability of TiO2. Okay, that's all my presentation, and thank you.
All right. Thank you very much, Dr. Kusama Griffin, for addressing this interesting topic. So, ladies and gentlemen, now we come to Q&A sections. Please mention your name before addressing your questions, and I will raise the questions from the Q&A box. Thank you.
Hi, maybe I start first. Totally. Yeah, hi, and Dr. Kusama, thank you for your presentations. Could I ask, like, how COS help to enhance the hydrogen production rate, since you show the performance is quite good from your results? What is the mechanism that the COS help to enhance the hydrogen production rate? Thank you.
Okay, thank you, Dr. Leo. Right, Dr. Leo. Okay. Actually, I'm sorry. I actually prefer for live presentation today, but I'm a bit trauma to see the previous plenary speaker. So last minute I request to I move to change the presentation mode to the video. Okay. Okay. How to improve a mechanism? Actually, you ask. Okay, can you see my PowerPoint? Okay, the mechanism actually. This is the mechanism of photocatalytic by the composite. We assume because TiO2 is n-type semiconductor and COS is p-type semiconductor. So
Bukannya lain Aina Anor.
okay, hello, can you hear my voice?
Yeah.
Okay, sorry. So if I'm sorry, I will not present in previous slide. Okay, if we see this mechanism, because COS is a p-type semiconductor, so the moving charge actually is whole, and the whole from the and for COS also photoactive, but not as good as TiO2. So we assume here whole from the COS will move to whole TiO2 to help the oxidation of water molecule. Meanwhile, the electron from the wide band gap, because TiO2 has a wide band gap, and maybe the electron not achieve the conduction band level, so some of the electron will move to whole of COS, and in at COS easier to move the electron to the conduction band, and the proton reduction will happen to the COS side. Okay, that's my answer, Dr. Leo.
Thank you for your answer. Yeah. Any other have any questions?
Hi Dr. Leo. Hi. Assalamualaikum Dr. Fuzaimah. My name is Aida. I have a question. In this water splitting, we need to prove that the hydrogen, right? Because after we split the water, we use our material and then we split the water, we must prove that we get the hydrogen. So in this research, did Dr. Investigate how much the volume as hydrogen was produced, Doctor? That's a question for me. Thank you.
Sorry, in my research,
Yeah.
okay, here we only just about 0.5, yeah, 0.5 millimole per hour per gram. That's the hydrogen rate we get. But in the study, we use hydrogen measurement by a homogeneous system. It's quite different with photoelectrochemical system. So the photocatalytic, the hydrogen production in homogeneous system actually higher than photoelectrochemical system, because the surface active area bigger than heterogeneous system in PEC. But we can just to show us that this composite is TiO2 and COS better than just we use TiO2. That's right. That's the question.
Yes, okay, Doctor. It mean in this case, use a heterojunction, right? The TiO2
Yeah.
is lower and the upper is the COS, right?
Yes.
Okay, so for the hydrothermal, what is the thickness for the hydrothermal, Doctor?
Okay, the thin film for the PEC.
Yes.
It's around. I'm sorry, I'm not remember, but not more than 10 micron.
Okay.
Because usually in PEC, the optimal thickness should be below than 10 micron nanometer. If bigger than that, the electron will not go to the the efficiency is very low because electron not go to the conductive glass, not cannot transfer to the contact electron.
Okay, Doctor. Thank you, Doctor.
So any more questions from the floor?
Okay.
Dr. Asmalina, I think she opened
think
the
you-
camera, but we can't hear you.
Yeah.
Yeah.
You have mute your mic, Dr. Asmalina.
Doctor, sorry to disturb. Dr. Asmalina, if it's the same issue as yesterday, just refresh your browser. Thank you.
While waiting for Dr. Asmalina, maybe I can ask one more questions.
Sure, Dr. Leo.
Yeah, for the ball milling process, you try to mill it using 3000 RPM for 2 hours. And then have you tried to lower down to 1 hour? Is it okay to get the nano size if you reduce down the time?
Actually, we have tried, but in this study we just report the best one because actually from the ball milling not too much significant the size from 1,300 RPM in 1 hour or 2 hours. But I'm mistake. I report here in the highest condition. Actually, the result from 15 minutes ball milling process is also similar to the 2 hours. But yeah, I see.
If the shorter time can get the nano size, then maybe for the real applications, then people will choose for the shorter time, right?
Yeah.
Yeah. Okay.
Better, more to efficiency for the energy actually. Better we use just 15 minutes right there.
Thank you. Dr. Aida?
Okay, Doctor. I don't have a questions.
Oh, okay. Is there any more question from the floor? Okay, if no, thank you, Dr. Kuzaima. Okay, now move on along to our invited speakers. Please welcome Dr. Nurul Aida. Okay, and the title is Electron Deposition of BiBio4 with needle light flower architectures for high performance photoelectrochemical splitting of water. Please welcome Dr. Nurul Aida. Thank you.
Okay, thank you. Let me share my slide.
Yeah, please.
Audience can see my slide right now?
Yes.
Okay. Assalamualaikum and very good morning to all the audience. My name is Dr. Nurul Aida and I am a postdoctoral research fellow in Nanocare in Malaya. And today I will present my research paper was published, and the title is the electrode deposition, which is ED, of a bismuth vanadate with a needle light flower architecture for the high performance PEC splitting of water. As we know, they have a lot of nanostructure have developed by all the scientists, all the researchers. For example, nanorod, nanowire, nanoflex, nanoplate, and nanotubes, and also the nanoflower. In this case, I want to show the beautiful of the nanoflower, which is I synthesis by using a material which is bismuth vanadate, which is the IVO4. For the application and splitting, water splitting. Also, actually, this is my nanoflower. It looks like a beautiful nanoflower, right? Okay, next. Okay, for the outline today, I will stress out about introduction until to the reference. Okay, this is the for introductions. Okay, the novel entitled by Lil Mysterious was the authored by the Jules Verne was expressed his viewpoint. Water will be the coal of the future. So this statement is especially relevant today because as we know the source of the coal we reserve, right, and we deploy in the next future. And now, as we know, the crude oil is the backbone of the energy demand and it's cover all the developing country and developed countries such as for the telecommunication, industry, transportation, and agriculture for the economic growth. So we need the electricity, right? This is very important right now. Okay, and now for that we must go to the renewable energy, which is in this case, for your information, for the renewable energy, we have solar energy, wind energy, and we have hydrogen. So hydrogen is we use to get the hydrogen, we use in this study, I use a semiconductor, which is my material, bismuth vanadate, to drive the water splitting for hydrogen production. And then as the novel of the PC water splitting was explored almost 40 years, where the pioneering work, which is our scientists, Fujishima and Honda was cited in the Nature manuscript in 1972, which is they explore the splitting of H2O, which is water, by using the hydrogen and oxygen using a TiO2. So they are the final of the water splitting by using a TiO2. And then why I chose the bismuth vanadate, which is Pvdf, because first it has become a popularity because they have high theoretical solar to the chemical conversion is almost 9%, and it's more dynamic active nature in the visible light. And then the pioneer of this material, this interesting, the unique of the material was developed by Fudo et al. They discover the photocatalytic activity of bismuth vanadate for oxidizing water under visible light. And then the uniqueness of this material, why I choose this material, because they have special band gap, which is small, which is 2.4 eV. It's more easier for the electron to transfer for the valence band and the conduction bands. In a semiconductor, the band gap is very important. So for the electron for movement, special of the bismuth vanadate because they have higher CB range, approximately around 0.02 versus RHE, and they have require a small bias potential to boost the photoelectrons toward the water reductions. And the last one, the uniqueness of this material, because they have a moderate hole diffusion length around 70 nanometer, that's allow for the efficient separation of photogenerated gas carrier. This is the introduction of the material, why I choose this material. Next. Okay, the next is this is several research paper have done by the other researcher, by other scientists. Okay, the first one is the Zhu et al. Was published in Catalysis today. He used fabrication of large size nanoporous bismuth vanadate photoanode. He used the printing light method and can be observed here. They have a nanoporous structure. The diameter is 150 until 200 nanometer, and then the photo current density achieved 0.75 milliampere. And the next is by the Chen and Lee 2018 in the was published in the Electrochemical After Journal. He used a nanorod monoclinic by bismuth vanadate nanorod array for the PEC water oxidations, and he used a seed layer effect on the growth of the Pvdf a nanorod array. Okay, in here we can see the beautiful of the Pvdf. He used a nanorod structure, right? And in this case, he used a spin coating. It's in a thinner layer on a seed layer, and the current density they get is 0.39 milliampere. This is look like a nanorod array structure. And the next is the research was done by Liu et al. 2019. It can observe that they have a nano-worm BIBO4 PEC sensor. He used a cyanuric chloride assisted soldier process, and this from the FISEM, they have shown the nanostructure like a nano-worm, and then here they get the 98.9 microampere and was published in International Journal Electrochemical Science in 2019. And the last one is the uniqueness and the beautiful of the use the nanostructure. It looks like a nano flower by Khan et al. 2017, used a sonochemical assisted hydrothermal synthesis pseudo flower shaped bismuth vanadate and their solar driven water splitting applications. This look like the what is called the nano flower of the structure bismuth vanadate. So all this show that every to develop a material BIBO4, they have used different technique, different method in order to enhance the PEC performance, and depends on the nanostructure. Okay, in my case, I synthesis bismuth vanadate by use a electrodeposition method, and I use the FTO as the substrate, and then I try to varying the deposition time is 1 minute, 3 minutes, 5, 7, and 9 minutes using the 3 electrode setup. And the last one, I want to investigate toward O2 and Hosh2 evolution to the pristine BIBO4 photoanode by using GCTCD, because right now, the water splitting, we need to prove that we can collect the hydrogens. We can see the bubble at the platinum, and then we want to measure how much we can get from the hydrogen from our semiconductor. Okay, this is my experimental. This is I made the 3 electrode setup. This is my conductive material. This one I use a reference AgCl, and this is my platinum. And in order to deposit of our material, I use the hot plate, and the hot plate is the temperature is around 70 degrees. And then I try to different the deposition time is from 1 minute, and it's lower. From the longer time is 9 minutes. So I variable that in 5 variable time. So we want to check the optimum one first. Okay, and then we try in this here, we deposit here in the FTO, and this is for the shorter deposition time. This show the film grow mechanism. For the shorter, we can observe the diameter of the FISEM by using the FISEM, and we can calculate the diameter our nano flower, and it's around or about 148 until 175.2. And then after we prolong the deposition time, we can observe that the diameter is getting bigger and bigger, and the diameter is around 333 nanometer until to the 449.7 nanometer. Okay, this is our bismuth vanadate photoanode. It look like a yellowish, a beautiful color. And then after we send to the FISEM analysis, we can observe color. We can present a looks like a middle light architecture. So this is actually the flower I get from the internet. I want to compare it with my flower too. So this is look like under the FISEM for magnification 500 nanometer. It look like a flower with a agglomerate structure. Okay, next we go to the result and discussion. I will discuss about a little bit for the FISEM, for the anti of the SPS. Okay, for the FISEM, I tried, if I mentioned, to differentiate the deposition time from the 1, 3, and 5, 7, and 9 meters. And we can observe here the deposited BIBO4 represent a tiny and long petal similar to the middle nanostructure, which is embedded closely onto the compact agglomerates. And then the thickness is playing important role. This is the cross section. This is the FTO. This one the FTO, and then this is can be observed that the thickness is mean bismuth vanadate will increase. This one, 1 minute, it represent around 110 until 121 nanometer. And then after we start to prolong the deposition time, the thickness will increase until that he reach the around 342.5 nanometer. So the cross section and morphology parameter govern the PEC performance. Okay, this is the check the roughness of our photoanode, which is bismuth vanadate, and then we use atomic force microscopy. In here, I use the FTO. It means substrate is in conductive material as a comparison to the my photoanode is 1 minute, 3 minutes, 5 minutes until 9 minutes. Okay, the roughness value of our photoanode increase is mean from the 21 nanometer until to 45.21 nanometer, but however, the surface roughly slightly decline around 42.89 nanometer due to the 9 minutes deposition because of the thicker layer. Okay, so this indicate that the optimum film roughness is achieved after 7 minutes of lateral deposition. Okay, this for the SRD, this is important because we want to check the crystallinity of our material after deposited on the FTO surface. Okay, this graph is a represent of the monoclinic bisvanate of a bismuth vanadate. So this here, I put the FTO. The FTO, they have major peak for the FTO. After we deposit, we embed our material from the 1 minute, and the FTO will decrease because the thickness of the bismuth vanadate will increasing, and we can observe that after we increase the time of the electrode deposition method, so they will increase also the crystalline of the in the SRD analysis. So it can be seen that the splitting of peak located at 19.9 degree with HKL number 0199, 200 and 240 predominantly exists in the monoclinic structure. And then after we prolong the deposition time lead to a stronger crystallinity peak and verify that a small interlayer spacing has a tendency for unimpeded transfer of photogenerated charge to occur that will enhance or empower for the photovoltaic activity. So the one is for 1:1 HKL number. So I make it larger so we can observe that after we increasing the deposition time, the size will be increases, so it becomes more crystalline for the BiO4 photoanode. Next, to check the bonding and the Raman vibration spectroscopy, I use this analysis. I use the FTIR, and then we can observe that for the FTIR, they have 3 peaks located around 300 until 900 wave number, and they have affiliated with the anti-symmetric and symmetric stretching of BO4 tetrahedral. And then for the Raman, they have 6 major parts. They have 6 peaks here. We can observe that. Okay, for the 8 to 7 is correlate with the anti-symmetric stretching mode of BO4 tetrahedral, and 7 they have a shoulder here located at 718 that sign to the symmetric stretching mode in BiBO4. So after we increase the deposition time, the peak also will increasing, and it show that the PEC performance also will increase. Okay, the next, because the BiBO4 is a photocatalyst light, because he absorb light to track as much of light to increase the photocarrier density. This is we use a UV beams and also the PL. It can be observed that all thin film show an absorption onset at lambda 516 nanometer, which is comparable to the report literature. And after we extrapolate, we use this equation to know how the band gap. So the estimated band gap using the dot plot, and then we can summarize that for the value of band gap for 1, 3, 5, 7 and 9 meter deposition time of the IBF4 are estimated around 1.52, 250, 246, and for the 9 minute is around 2.5. 2.41 EV, and this one for the PL, as we know for the PL we must have a lower PL intensity because it corresponds to the higher photo-induced electron and hole pair separation efficiency. Okay, this is for the PEC performance. For the PEC performance, I try to stress here we doing the analysis for the back and front illuminations. These findings is the back illumination photo current density compared to the front illuminations because they have easier for the hole diffusion than the electron diffusions. So this is the standard deviations. It means the samples was done in a 3 triplicate of sample. So this is the potential versus RHE versus volt for this year 1.23 volt, and it show for the back illumination show the highest around 0.32 milliampere. So this one is a chopping. It's been to prove that our photoanode is visible light and can active photoanode under visible light and for under light and under dark light. So this one is the resistance for the PEC. We need the low charge transfer here because for the lower charge transfer, they have lower resistance between electrolyte and the photoelectrode. It can be observed that the 7 minutes deposition time have a lower charge transfer. The 1 minute, they have a higher charge transfer for this photoanode. This one for the interfacial charge transfer efficiency. Okay, based on the analysis, is proof that at the 7 minutes we have the higher photocatalicity and we have the higher charge transfer efficiency around 66.7%. Okay, next the SPS. The SPS analysis is important because we want to check the elemental analysis. Okay, for the SPS, the sample was tested before and after we run the chrono analysis, the stability test for 30 minutes, the sample was tested by the SPS because we want to show the the oxidation in our sample during the stability test was run. So based on this finding, it can be observed they have be different here in the oxygens because the peak intensity located at 531.1 EV slightly emerged, which is attributed to the oxygen vacancy after the chronoamperometry experiment. We can prove that during the redox reaction, the oxidation process can occur in our sample. And we can summarize that the intervention during the oxidation process in a pristine can contribute to the oxygen atom. Okay, the next is the O2 and H2 evolution. This is important part right now in water splitting. We need to prove that we gain the hydrogens because during the redox reaction, the splitting of water can produce the hydrogen, right? We want to calculate how much we can get the hydrogen. Okay, based on this analysis, I run for the 3 hours in the reactor, like a chamber. And then the gas was collected and measured at constant potential 1.23, and based on estimation, we get the oxygen, hydrogen and oxygen like 39.72 and 20.23, and we can assume that the O2 and hydrogen evolve around 2, which is the Faraday efficiency, nearly around 71%. Meaning that oxidation occur at our photoanode and the reduction occur at the platinum. So this is photocatalytic mechanism. We want to know how the valence band. So for the VB, we get from the analysis. For the SPS, we extrapolate here, and then for the band gap, we can create the. So we can by the simple measure, the CB is around negative 0.54. So this is how this process mechanism of photocatalytic mechanism. Okay, for the last, the conclusion here in the photocatalytic achieved here around 0.32 milliampere, and then he used electrolyte and O2SO4 as deposition time increase. So we can observe that for based on the SRD, and then according to Raman also, they have obvious increment in the peaks intensity when we manipulate deposition time, and the comprehensive discussion as point out in this study will encourage the progress in the field of nanotechnology and material science by widening the opportunity for the forthcoming development of efficient optoelectronic device with a various nanostructure. So this a little bit reference I use in this research, and for more detail you can read in my paper, and don't forget to cite that. Thank you.
All right. Thank you, Dr. Nurul Aida, for addressing this interesting topic. Ladies and gentlemen, is there any question from the floor for Dr. Nurul Aida?
Hi, Dr. Nurul. Juan here.
Yeah. Yes. Hi, Dr. Juan.
Hi. What is your STH, solar to hydrogen efficiency?
Solar is the what is called efficiency, right?
Yeah, STH, solar to hydrogen.
Solar to hydrogen, based on I use the interfacial charge transfer around 99.7%, doctor.
Basically, if nowadays want to study these hydrogen productions, you need to calculate the solar to hydrogen called STH. You should think of it how to calculate the STH. Without STH, I think hard to accept the paper nowadays.
Yeah,
it's quite saturated in the field. You have to look at the STH, solar to hydrogen. Yeah.
Okay.
All right, thank you, Dr. Juan. Any more questions from the floor?
Hi, thank you for your presentation, Dr. Aida.
Thank you, Dr. Leo.
Yeah, could I ask some questions about your nanoflower? Have you done any TEM? Because from the FECM, the images that you showed just now, maybe it's a low resolution. I can't see is a nanoflower. Yeah. Have you done any TEM or the high resolution of the FECM?
Actually, this research was done in the UKM before my PhD, but for the TEM, we have it, but to fulfill the requirement for the TEM, I don't have it because we cannot access to the lab. So this is very limitations. So I just proved it by the FECM, doctor.
Yeah, maybe if you have a higher resolution of the FECM, then maybe you can see really the spike, the spiky surfaces.
Yeah.
Okay, thank you, Dr. Aida.
By next time, I try to analysis by using STEM. Thank you, doctor.
Yeah, thank you, Aida.
All right, is there any more questions? If no, thanks again, Dr. Nurul Aida, for your presentations. Now move on to our next invited speaker. Please welcome Associate Professor Dr. Juan Jun Cheng. And the title is Highly Active Oxygen Vacancies of Nickel-Dot SRTR03 as Cathode for Rechargeable Alkalizing Battery. Please welcome Dr. Juan.
Okay, thank you. I try to share my screen. One moment. Okay. Okay. Okay, thank you, Dr. Lee, for the kind introductions. So I'm Juan from Nanocat, UM. So today I will share with you is the use of a perovskite material as a cathode material for this rechargeable alkaline zinc battery. So this is the agenda. So I want to know about the importance of battery, right? Okay, from the using the clean energy, and the storage of this clean energy. So we need to have a good battery, high capacity battery. About global market of these batteries, everyone knows it's too important. How big is this market? It's basically about $19.4 billion by 2024. So it's very important energy storage systems nowadays. You can see all our gadgets, including these laptop, are powered by the what you call battery, okay, and your handphone and so on. I think this driver increasing demand on the transportations, electric car. But the challenge here is the material scarcity and the safety issue and also the cost. As we are aware, current battery are heavily dependent on the lithium. So there are some issue about the lithium because we heavily depend on the what call lithium. They'll run out in one day. Secondly, lithium, as we understand, is very active and is a lot of cases time to time have cost explosions. So there's the opportunities for this what I call technology enhancement and usage of the hybrid and electric car. So in this what I call presentation, I will share the using of a rechargeable alkaline zinc battery (RAZB) become a very attractive to a lot of researcher because the performance is very good, it's safe, low cost, and more environmental friendly. I'm not saying totally environmental, but more environmental friendly because we need to diverse, not only depend on lithium, but other material, other metal as well. But however, the road of these commercializations is still lacking because of the first is the active material and second is the poor stability. That means the recyclability of this rechargeable alkaline zinc battery is very poor. Hold on, someone click on my. Okay, sorry. Something ringing on my bell. Okay, so where are we now? So yeah, rechargeable alkaline zinc battery is very important. So this is what we get from literature. So we can compare what are the current trends about this what we call rechargeable alkaline zinc battery. So basically, you can see that the energy density, the highest is can go up with to 15.38, and also the capacity is 114. Okay, and the cycle is quite good, but again, the energy density and capacity is quite low in this sense. So there are room for improvement. So we venture into perovskite. Why we choose perovskite? First, because it's highly stable, thermal and also chemical. Second is layer structures. This is the main conductivity will be very good. Good redox behavior, and one is the issue of this poor electric conductivity depend on the material itself. So the introduction of oxygen vacancy. Basically, what we are intend to do is we can improve this by having the oxygen vacancy. This is the advantages of among all these perovskite material, we choose the scandium TiO3. Okay, so we have do some literature and found out the SrTiO3, one of the perovskite material, is good potential because it's high redox actives, high thermal stability, and it have cubic structures. And we also have used in a fuel cell because high chemical resistance, strong resistance in carbon dispositions, tolerance to sulfur poisoning. Of course, in our battery, no such thing. But based on the literature, just good show that good chemical stabilities, and also containing some of this oxygen vacancy. Of course, the oxygen vacancy is not what we call well studied. That's why we have this idea to introduce the oxygen vacancy in the perovskite material. So what we're going to do is the scandium TiO3 have a specific capacity of 24.8. Okay, we have managed to use this scandium TiO2 in our batteries, and what we need to do is do some dopants 52.7. That means what happened in the literature, they mentioned that the SrTiO3 with the specific capacity of 24.8, after doping with platinums, it can increase to 52.7. So it's about 2 times. That means there are potential for us to further improve this SrTiO3 by using a dopant. So this is the potential dopant that we have done actually. Okay, the students also writing their thesis. So we have choose these three potential what we call dopants: nickel, aluminium, and manganese. So today we will just talk about nickel itself. So this is the problems. Most of these material, zinc, rechargeable alkaline zinc battery, are using nickel oxide, cobalt oxide, bismuth oxide. They have saturated. There are no more what we call improvement. People have tried a lot of others methods and material and doping and so forth to improve the charge capacity of this material, but it's still lagging behind. So they have material have advantage of why do people choose this material? Because they have multiple valence states and high stabilities. So do the perovskite that mentions, okay? But perovskite haven't been used before. So we have this ambitions to try using a perovskite material. So this is the objective. Using this perovskite material, what we want to do is synthesize this SRTO3 using simple methods, hydrothermal methods, right? Just put everything inside and put into hydrothermals using a temperature to manipulate the structures of SiO3. Of course, we want to improve the conductivity. As mentioned just now, SiO3 is quite poor in conductivity, even they have a layer. So we have to do something to improve this conductivity, and we choose nickel. Besides that, we also have this opportunity to increase the conductivity by introducing this oxygen vacancy, which is poorly understood, but we want to try better by having the oxygen vacancy, the conductivity of this SiO3 is it improved. And we also want to study the mechanism. So I don't want to go in detail. This is a very simple process. You put all the precursor inside and put into the ovens. The hydrothermal temperature is varied from 120 degrees C. This, of course, the normal characterization we need to do whether the material is properly synthesized, and then we assemble our batteries, right? So we have this Si3O3 cathode materials and the zinc plate as anode material, okay? And the electrolyte is KOH and the bit of zinc oxide. So then we test this performance using the CV, GCD, and EIS. So what we found here, first we have to synthesize this what we call SRTO3, okay, at 120 degrees C. You may ask why we choose 120 degrees C, because this is the best temperature to produce the scandium TiO2 with a good conductivity and good what we call capacity. We found that at the 120 degrees C, we're able to introduce this oxygen vacancy that enhance what we call the current or current density. And then we have do some doping here. We vary the what we call concentration of the dopants from 1% to 5%. And you can see from here, from this XRD, we managed to synthesize the STO, okay, or the scandium TiO3. And after dopant, the structure did not change much. So this is good news, did not change much of the structures, still remain as a perovskite material. They did not destroy the scandium TiO3 material. So, but doping of nickel in the host material cause the increasing of range growth and lead to a larger crystal size. This is what we observe because the broadening of the XRD peak show that this crystal size become bigger. Okay, you can see from here unit cells, okay, become slightly bigger, okay, from 60 to 62, 63, okay. And then look at the SEM result and also the particle size distributions. It seems that the of course when we have the dopants, it really affect these particle size distributions and also align with the XRD result. Then we run the BT to look at the surface area, and we found that the mesoporous type 5 material, okay, with H3 hysteresis, so it's a mesoporous material. Fortunately, what I call the structure still retained. It's a good thing that the structure is retained. That means the surface area is also retained. You can see from here, the surface area is retained, slight reductions only. From SPS, this is very important data. the nickel doping caused, right, the oxygen vacancy increase in the order of 3%, more than 1%, and more than 5%, and more than STO itself. This show that this nickel is not only as a dopant, but induce this oxygen vacancy. So I will show you why this oxygen vacancy is very important later on. And then the look at the performance, because we have to test the performance, because we want to see the capacity or the specific capacity of this battery. So the 3% seem to having this high what we call specific capacity, about 596 milliampere per cm cube, okay, as compared to others dopant and also the STO. Okay, so it's increased about it's not near, but about near to 2 times. So this is a very good what we call materials. This is the what I'm saying, that the mechanism here. What we've found out that in the first report, this is the first report, the using this perovskite material, it can be used as a cathode material for this rechargeable zinc battery. On top of that, we also first report on the importance of this oxygen vacancy in the battery research, which is poorly understood previously. By introducing this what we call oxygen vacancy, actually the this means that lacking of what we call the oxygens in these lattice structures. For example, here it should be have oxygen atoms here, but it's lacking of these oxygen atoms. This affect the neighbor atoms. For example, Ti3+. Ti should be a 4+, but due to this oxygen vacancy, to balance the charge, the Ti become a 3+, because they have donated 1 electrons to the oxygens, so it become 3+. And similarly to the nickel as well, so it become nickel 2+. Okay, so when we have a charge mechanism here, what happened is the Ti4+, okay, because we have electrons here, okay, he have been introduced, so become Ti4+. So this is a charge-discharge mechanism. So they increase the probability of having more electrons. As we understand, more electrons means more what I call capacities. So this is what's happening here. So charge and then discharge, okay? To balance it out also, because we have this electrolyte, so this one also balance out the water molecule here, okay? So this one is the advantages of having the oxygen vacancy. So this is the first mechanism that we propose and have been published so far for the anode and the cathodes, using this what we call rechargeable alkaline zinc battery. So we also do the what post-mortem means. We do after the charge, okay, charge discharge, after several cycles of discharge, we analyze what happened to the material, okay. So it's reduction of lattice oxygen 529 eV in the SrTO3 in charging state due to the base oxygens. So this also proved that after the material, right, charge discharge process, also release this O2 minus. Charge compensation occur due to formation of SR vacancy coupled with formation of SRO layer. So this is a good things for the battery, because they're able to balance the charge, because a lot of material, when they charge discharge, they tend to destroy the structures because they don't have the what we call the vacancy to compensate with the charge and discharge electrons. So having a bit of this oxygen vacancies, it could, right, it's good for the this mechanism charge and discharge. And the Ti3+ peak increase in charging state, indicating OH ion is integrated, as mentioned just now. Need to balance up the charge. Also, the mechanism always involve this hydroxyl ion. Ti3+ and I are oxidized to form a Ti4+ and nickel 3+ upon charging, vice versa discharge. So as mentioned just now, so these charge discharge issues have been resolved. So they can charge and discharge in a very stable form. So we have these what we call restricted discharge capacity, and the RCT value means the what we call the resistance. Okay, so it is quite good news that we have a very good what I call the charge capacities of nickel. Okay, I'll show some work on aluminium itself. Okay, aluminium is definitely the best lah. Okay, but I do want to discuss in this what we call presentations. So this is what we report here so far. This is the previous studies, okay, by others, okay, using the nickel oxide, the common type of cathode material. So we have a first report using the perovskite material, STO, we can become much better, okay. It's about 2 times better than the previous report result, okay. And this nickel STO, what I report today, is much better than STO. So it's about 60, about reaching 60. The energy density is in 60 milliwatt per cm cube. So this is the comparison with others. So Incogrians will successfully prepare to very simple methods, so it's easily scalable. Definitely the nickel itself have improved what we call the resistance or conductivities. Okay, we have the reduced the resistance and increase the conductivities. On top of that, this also exhibit high specific capacities, about 600, and 65% higher than the previous STO. This is because the doping have induced more oxygen vacancy and increased the electric conductivity STO. So this lead to a rapid diffusion of ion toward the electrode, which contribute to the high capacity. So this is the reference. I want to acknowledge my students, Christel Wong. So she is writing the thesis, should be graduating soon. Then others are my students and my also others colleagues. Thank you very much.
All right. Thank you very much, Dr. Joan, for addressing this interesting topic. So is there any question from the floor? The expert is here. Please ask. Is there any question from the floor? Yeah, Dr. Leo.
Hi, Dr. Joan. Thank you for your excellent presentations. Because I know from this background, maybe I will ask some general questions. For example, just now you say there are already a rechargeable alkaline zinc battery in the market, right? So how about your technology compared to theirs in terms of the costing? Yeah.
Basically, you can see, I can show a bit of this. You can see from literature here. Let me see. There's the problem. Okay. Can you see the screens? This is a common material used by people: nickel oxide, cobalt oxide, and bismuth oxide, right? Actually, is what we call rechargeable alkaline zinc battery. Actually, is in the market. Actually, correct. Okay, and they're using nickel oxide, cobalt oxide, and bismuth oxide. But they are not. You cannot see them using in the what we call. They use in a small what we call a gadget. Okay. Is my calculator or some 3A, 4A batteries, because the energy density is not that high. Okay, so they are using nickel oxide, cobalt oxide, bismuth oxide. You calculate the cost using the scandium TiO3. Okay, scandium TiO3. This one by itself is almost comparable with this nickel oxide, cobalt oxide, and bismuth oxide. You see, bismuth oxide is not cheap though. Bismuth is not a very common material. Same with cobalt, okay. So in terms of price, it's almost comparable, okay. But in terms of capacity, you can see from our research here, it's already much more higher. It's about 2 times higher than the current reported in the literature, okay. So why we put the nickel here? Because we want to increase further is what we call the energy density and also the capacities. So in terms of price, it's comparable. But in terms of manufacturing these ones, again, this is what we need help from the industries. As a scientist or researcher, we do not have the capabilities to manufacture this material in bulk. Okay, that's why I also emphasize on the using a simple method, so people from the industry can adapt, use our technology for commercializations. If we use a very sophisticated methods, it takes times for commercializations. Of course, sometimes we need to have a complicated method, Okay, but try to get a simple one first for our research.
Or the next
for
one,
real application, yes.
have you tried with like charge discharge? How many cycle?
Yeah, we
done?
tried about 100 cycle, only 100 cycle.
100 cycle. Okay.
But we did not found any what we call reductions in the charge capacities.
Up to 100 cycle.
Yeah, up to 100 cycles.
That's very good.
It's very common in the batteries, 50 to 100, or people sometimes go for 1,000. Okay, so it's a very common practice in batteries that people try 50, 100s. Okay.
Yeah, thank you, Dr. Chuan.
Yeah, Dr. John, one question from Dr. Asmalina. Okay, Dr. Asmalina is asking what else variables can be explored in order to improve the performance of the alkalizing batteries?
Yeah, this is a very good question actually. What can be done here? Okay, so it's the first time that we found this oxygen vacancy able to improve what we call the performance of this perovskite material. Then the questions arise, how about other material? Okay, how about other material? If we can induce this oxygen vacancy, would it also applicable for other material or become much better? Okay, so this is the questions. Okay, that's the what call, we have started something. This oxygen vacancy is very good for the batteries, so we can explore and venture into other type of material. Okay, by using this concept of oxygen vacancy.
All right. Thank you, Dr. John. Is there any more question from the floor? No more? All right. If no more questions from the floor, thank you, Dr. John. So now I would appreciate if everybody can turn on the camera for another photo sections due to just now Dr. John is not available at the initial sections. Dr. Asmalina, Dr. Kuruzama, Miss Aminato. Oh yeah.
Hold on, we have a new addition.
Prof. Anjev.
Okay, I will take the picture now. Okay, just a minute. 1, 2, 3. Okay, thank you, folks.
All right. So before I end the sections, I would like to announce the best presenter for these sections, photochemistry and electrochemistry. All right. So, Lokman, ready?
All right, coming up. Doctor, you can announce the winner.
Okay, so the best presenter for this section, photochemistry and electrochemistry, goes to Dr. Kuzama Arifin. Congratulations. All right. Thank you, everyone, for attending these interesting sections for the chemistry and electrochemistry. So I will end these sections. Okay. So hope to see you next round. Okay. All right. So thank you very much.
Thank you all.
Thank you.
Do stop by the networking station. Thank you.
Thank you.
All right.
Bye-bye.
Thank you, Dr. Morris.
Thank you, Dr. Good job. Thank you.